Okay, so let's take a look at today's lesson. We're going to be looking at area and rotational speed, a couple of different concepts for us. First of all, let's talk about area. We are accustomed to finding area of a sector. You would have done that in geometry, right? You would have found the area of the circle, determined what portion of the circle it was, and then multiplied by that, right? That's what how we have found areas of sectors in the past. In pre-calculus, we actually have an alternative way to do that, another formula. It's area equals 1/2 r squared theta. The critical thing for us here is to remember that theta has to be in radians. If it's not, we have to convert it. So that is a big caution, really the only caution. Of course, you're going to need to memorize the formula. Area equals 1/2 r squared theta, and it simply just finds the area of a sector for us, given that the central angle is in radians. And we'll do an example of that. The second concept that we're going to be looking at today is rotational speed. Let's just kind of skip straight down to here and look at how this is set up. So rotational speed, this is at the equator. We're talking about rotational speed of like the Earth. I think maybe in the daily work I have something about Jupiter. I mean, there's just of a large mass. So this 2 pi is our angle measure. I'm just kind of walking you through this. Hopefully you recognize 2 pi is the angle measure. This is radius. So we have we have theta times r divided by time. 24 hours. We should recognize that formula. Theta times r divided by time. That is our linear velocity formula, isn't it? That's all that is. So I've actually had a lot of questions about this. I was taking it for granted that we knew why it was 2 pi, but some students don't, and why it's 24 hours, but some students don't. So I'm just going to make sure we understand. So what we're doing is we're calculating how fast the Earth is rotating. We want to look at one rotation of the Earth. One rotation, it turns around one complete time. That would be an angle measure of 2 pi. Right? It doesn't matter how large the object is, as long as the rotation is one time, that's 2 pi. We're in radians. Now, when the Earth rotates one time around, that's in a 24-hour period. Right? It rotates one time around, and we're just general. We're not being perfectly exact, but one time around is 24 hours, which is why it's 24 hours and it's 2 pi, because we're looking at one time around. Now, do we have to calculate the rotational speed of the Earth using one time around in 24 hours? No. You can do really anything you want. I mean, but why would you want to do like a half turnaround and do 12 hours? I mean, you could, but again, we're just trying to make it easy, right? One rotation of the Earth, 2 pi, it happens in 24 hours. And we're using 2963 as the radius of the Earth. And when we do that, we actually come out with something I think is kind of amazing. If you are standing on the equator, the Earth is traveling at over 1,000 miles an hour. I mean, that is like, wow to me. What would happen if the Earth just suddenly stopped spinning? We would be in really big trouble, right? If we're going 1,000 miles an hour or wherever we are and then it suddenly stopped, that would be a problem. So that's basically the rotational speed of the Earth at the equator. What we're going to do is we're going to find the rotational speed at other places besides the equator. Let's think about this for a second. If we're looking at a space, I'll just give you an example. So, we know what the speed is here at the equator. What if we, went up here? Okay, what is that going to have the same? Is this location on the Earth going to have the same rotational speed as the equator? And it's not, is it? Because the rotational speed, this formula, relies on the radius. And the radius here is not the same as the radius here, right? This radius is different. So we're going to learn today, we're going to calculate the new radius, and we're going to find, rotational speeds at different locations. Okay, any questions so far? Okay, let's jump into our examples. We'll just flip to the next page. Our very first example has to do with area. We have a sprinkler on a lawn is set to spray water over a distance of 70 feet and rotates through an angle of 120 degrees. So I'm always going to be drawing. It's important. So we have 120 degrees and our radius is 70 feet. Okay. find the area of the lawn watered by the sprinkler. So basically they're asking us to find the area of that sector. So we write down our formula, A equals 1/2 r squared theta, and we simply plug into the formula. A equals 1/2, r happens to be 70 feet, right, squared. Theta is 120 degrees, but am I allowed to use degrees in the formula? No, so I have to convert. Now I really recommend that you just leave it all in a string and just put the conversion here at the end. Because the work that I'm going to need from you on a quiz or a test is I'm going to need you to write this out like this and then just put it in your calculator and give me the answer. That's it. Write it like that, give me the answer. I don't need to see any other work. That's the standard for us on the AP Calculus test. You have to write out, your formula, whatever you're using, with the numbers in it, and then the answer. So we do that, and we learn that we are, the area of the lawn is 5131.268 feet squared. Okay, and that's the area that is being watered. Okay, we okay with that? Okay. Let's take a look at number 2. Asks us, what is the Earth's rotational speed at Durham, whose latitude is 36 degrees north? All right, so here we go. Let's do our rotational speed thing. So I have the Earth. We'll put Durham, up here, wherever. So that's the location. We're going to need a radius, right? That's what we were talking about just a few minutes ago. That's r. I need that little r. So I'm actually going to make a triangle. Okay, and just for ease in looking, I'm going to take this triangle. Let's just I'm going to take this triangle right here, and I'm going to pull it out so we can really look at it a little bit better. So there's my triangle. I've enlarged it so we can see a little bit better what's going on. That's our r. We know that this is 36 degrees, right? That's our latitude. That's that central angle right there is 36 degrees. Hopefully we remember some geometry here. So we have 2 parallel lines. So see my 2 parallel lines here, cut by a transversal. So we know if this is 36 degrees, so is this. Okay, we okay with that? Here's our 2 parallel lines cut with a transversal. We have alternate interior angles. Those are equal. So here's my 36 degrees. I can use that angle if I want to. I don't have to. What if I wanted to use this angle? I could do that, right? We know that total is 90 degrees, right? So 90 minus 36 gives us 54 degrees. So I have some options here on how to find r. The other thing that I know is the radius, this right here, that's the radius of the Earth, right? And we're using 3693. Okay? Or 3963, sorry. We're using 3963. All right, so I have some options here. I'm going to use 54 degrees just for fun. And then r is opposite. So if I use 54 degrees, I'm going to be needing to use sine. So I would say sine of 54 degrees equals r over 3963. Now, I'm just going to pause here for just a second. If I wanted to use 36 degrees instead of the 54, I could, right? That's okay. So if I wanted to use 36 degrees, r would be adjacent. So I wouldn't use sine, would I? I would use cosine. I would say cosine 36 degrees equals adjacent, which is r over hypotenuse. So I just want you to understand it doesn't really matter to me which way you set it up. Either way is fine. It's whatever you prefer. Okay? So now let's find the radius. We would need our calculators. And so we're going to do sine 54 degrees times the 3963. Now, in the previous class, I've had some questions about storing numbers. There's a little bit of a confusion on storing numbers in our calculator, so I'm actually going to go through the calculator portion just real quick. But to do that, I'm going to have to erase over there. Does everybody have what they need up here? Okay, so what I'm going to be doing is I'm going to be calculating this part right here. So let's get to our calculator. It's important to understand how to store numbers, because what we do is we're basically given the most accurate representation. We always keep all the numbers in our calculator. You're probably familiar with that. I'm hoping from previous math classes, but we're always going to keep everything in the calculator. So first thing we need to do is do sine of 54 degrees. Now we would have, like tomorrow, I would have reset your calculator. You would have. When your calculator resets, it resets to radians. Because that's the coolest one, right? Radians is the best, so of course it's going to reset to radians. But that's not going to fit, we need it to be degrees. So we would go to our mode, and we would check to make sure our mode is in degrees, okay, before we put it in, or we're going to get wrong answers. I just want you to be cautious. Okay, we need to be in degrees, so mode, go to degrees, you just scroll down, highlight degree, hit enter. All right, so let's get out of here. So now I'm going to type in sine of 54 degrees times 3963. Okay, so this right over here is my radius, right? It has all these numbers in here. We don't want to have to be responsible for typing in all those numbers. We could mess that up. So what we're going to do is we're going to store it. To store this number, we hit this STO button right here, store, and then we decide where to put it. Never, ever, ever put it in X. Don't ever put it in X, because this X changes all the time. And I'll show you. If you hit X right now and hit enter, there's going to be a number in it. Whatever the last number that you used on your, sometimes if you do intersections in your grapher, there's a number in there. Maybe it's 0. There's some number in there. So it's very dangerous to store in X, since it's going to continually change. You need to pick another variable. So I usually store in A, alpha A, B, or C. That's where I usually store. Store where you want. So alpha A is where I'm going to store that value. So now if I wanted to use that value, I would just hit alpha A, and then it would give me that value. Okay, so it's stored there. So what do we need to do? We need to do our formula, which is 2 pi times, that gigantic number, over 24. Let's look at some more calculator input. So we're going to do alpha y equals, enter. Right, the fraction thing that I showed you before, alpha y equals, enter. We're going to type in 2 pi, and then we're going to put an A there, because it's 2 pi times the radius, right? The radius was A. We put it in A. So A over 24. Is everybody okay? Then we hit enter. And that is the speed. It's 839.364 miles per hour. Okay, so 839.364. Are we all right with that? Okay. Calculator stuff good? All right. Let's go back. So let's look at the third example. So we have, at what latitude is the circumference of the circle of latitude at P half the distance around the equator? All right, so this one's an abstract problem. We need to get, more comfortable with abstract problems. So I'm going to be throwing them at you from time and time again. So we don't know where P is. I'm just going to pick a place because, I've got to draw things. There's P. We want to know, what do we want to know? We want to know that this location right here, this radius, is half of the radius, right? We want it to be half the distance around the equator. If the distance around the equator is R, we'll call that as R. So let me pull this out so we can see it a little bit better. Okay, so this distance is R. We know that distance is R, right? Then we want it to be halfway, so this would be half R. Okay, my latitude, this is my latitude, my theta, and this angle I'm going to call alpha. I'm just going to use that as a helper angle. Alright, so I'm going to do sine of alpha equals opposite, which is 1/2 r, over hypotenuse, which is r. Let me pause there for a second. I'm setting up a trig ratio. We okay with that? So sine of alpha equals 1/2 r over r. Notice how the r's cancel out. So basically sine of alpha is 1/2. So we need to think about where is sine 1/2. Let's think about the unit circle. We really only are caring about the acute angle where sine is 1/2. Remember that? That's 30 degrees or pi over 6, whichever mode you're in. Latitude's in degrees, so that's at 30 degrees. So we know alpha is 30 degrees. So we know this right here is 30 degrees. Is that our latitude? No, that's just like a helper, right? Our latitude is theta. So theta is actually going to be 60 degrees. So the answer is 60 degrees north in the northern hemisphere, or 60 degrees south in the southern hemisphere. That's where this particular concept would be true. Okay? We okay with that? All right? Because what angle measure is sine 1/2? Right? The angle measure sine 1/2 is at 30 degrees. Okay? Anything else? All right.